Guys who work here, why are you telling them to this or something? This is not allowed. You have to allow talking about English. That's totally different.
Okay, thank you everybody for being here, and special thanks to our online audience who have been waiting patiently. I was told that this was muted, but I guess you've been listening in on our tidbits. Anyhow, welcome all of you. So we are extremely delighted to have with us Dr. Adnan Bashir with us today. This is going to be the first, so this is kind of like the beginning of our celebration of 100 years of Salam. And it was just a lovely coincidence that Adnan was here for visiting the NCP in Islamabad, and he was gracious enough to actually volunteer his services to come here and deliver a talk. Adnan is currently working at the University of Huelva, and he completed his PhD at the University of Durham. He has been involved in uh, uh, setting up schools of particle physics in Central America, and has published numerous articles. He is a very frequent visitor to Pakistan and indeed the world over for all kinds of talks. I am basically just going to hand over to you right now, but I will just say one thing. Salam's work is spans a lot of areas in particle physics, and there are several aspects to it. You're going to see some of those aspects in today's lecture, and in subsequent lectures, you will see other aspects of Salam's work, and also how people are continuing to work on some of those ideas that Salam helped develop. In addition to this, please be on the lookout for a special session that we're going to have at some point in the future, where currently I am contacting people who have been who had been working with Salam, both professionally in terms of his scientific role and also his role as an administrator. So people are already sending me some videos of their interactions with Salam. So we are going to showcase those in a special session later on this year. It's a wonderful time to now hand over to Adnan. Thank you very much.
Does it work? I don't know if it's on. Is it working? That's only for the Zoom.
This is only for recording. The Zoom one is right here. So that's
for recording, not for.
Yeah, this is not for the people here. Yeah.
Okay. I'll probably start with a couple of apologies. I can see here people are very specialized, some of them in particle physics, and some have absolutely no clue about that, and they're not even physicists. So this talk is going to be very technical for those who do not know physics, and this is going to be very trivial for those who do particle physics. So it's not going to please anyone, but that's fine. Secondly, about Abdus Salam, I never met him personally. I've had an indirect way of working on what he has worked on. I just once wrote him a letter and he graciously replied, but that was the only communication I had when I was a student. But I'll tell you in what way my work is connected to what he has done over the years. So it was, this talk is not really very much going to be about Abdus Salam, but about his work and how particle physics gets connected or benefits from what he has contributed over the years in different parts of particle physics. So I'll start with a few things, only some of his main works within the realm of particle physics. I think he's mostly known for what is called the standard model of particle. Standard model of particle physics, which deals with every fundamental particle that we have come to know and all possible interactions that they undergo at the fundamental level. Okay. So the standard model of Salam, Weinberg, and Glashow, which continues to be the standard model of particle physics since the early 1960s. has explained almost everything that we so far know in the field. So that was given first by Glashow in 1961. Glashow's model had the right symmetries of the model, but it could not incorporate the masses of the particle. The theory did not remain inconsistent, but that problem was stated. So you probably have to mute someone.
Yeah. Can I request everybody to please mute yourselves? Online audience, please mute yourself. You carry on. I'll take care of it.
Okay. It was given by Weinberg in 1967 and Salam in 1968. They made several predictions. One of them was what is called the weak nuclear currents, the existence of W bosons, Z bosons, and Higgs boson. Higgs boson is probably everybody knows the quad particle, which was discovered in 2012. The first prediction nuclear currents was detected in 1974, after which they got the Nobel Prize in 1979. Even the existence of W and Z particle was done years later in 1983 and 1984 by, what's his name? Carl Rubier. And this picture is in fact Abdus Salam hugging Carl Rubier, who had recently made the discovery of W and Z particles in 1984. And that is that he came to visit ICT, Salam's Institute for Theoretical Physics. He, I think this has got disconnected, so I can't go forward.
What's disconnected?
I think you have to just click onto the main screen and then I can.
Sorry,
yeah,
there we go.
That's fine. So he had worked on many other things than what are called the grand unified models. Some people, including Salam, at some point thought that all the fundamental forces can be unified in a single Lagrangian. So one of the first models at that time was given by Salam himself along with Patihi. They wrote, I think, 2 papers, one in 1973, one in 1974. Both are very well cited. I think one of them has citations of more than 3,000 or so. So that was one of the first unification model in which lepton was considered as one additional color than the quarks had. And it also had the right-handed neutrinos, which means it was one of the first things which gave this possibility of neutrinos having masses. So I will not talk about this grand unification model. I think Rizwan himself works a lot in it, and there may be other people in the field. Anyway, so far, we don't have experimental verification of any of these grand unified models. Then there's another field of supersymmetry. People thought that there was this fermion gauge boson symmetry, which led to supersymmetry. It was not invented by Salam, but he gave a particular formalism in which fermions and bosons were put in one supermultiplet. And that work he did was with one of his students, Strathi, who was a student at Imperial College. But when ICTP was made, Strathi came with him to work at ICTP. In fact, he didn't even finish his PhD. He just went on to work with Salam. And he continued to work till Salam passed away. And when Salam passed away, he stopped doing physics and went back to New Zealand. He was originally from New Zealand. So this work is one of those works which is not very well known, even among some established researchers. I don't know, those who do particle physics know something called Nambu-Goldstone bosons. When a continuous global symmetry is broken in quantum field theories, that leads to the emergence of massless Goldstone bosons. Okay? And those in this case are pions. But that idea was originally given by Nambu, I think, in 1960s. Then Goldstone worked on it. But then finally, Goldstone, Salam, and Weinberg together wrote an article in 1962, which was a formal proof of that conjecture, which was made earlier by Nambu and Goldstone. So that's quite an important work. So I will be talking a little bit about this. This is quite important in what I'm going to talk about. And finally, which is not visible at all here, is the most important thing that I'll be talking about. That is also not known much. So if I get, no, can we go back to
Yeah.
the slide? Yeah, okay, thanks. I can do that. I think I'm going a bit slowly because I know that there's non-particle physics people, so I'll probably not take an hour. It will last for 2 hours, 2 and a half.
That's fine. I'm here.
Okay. So as I mentioned to you, I never worked with Salam directly, but when in 1999 I went to Adelaide for a LightCon meeting, I met Dilbergo, his student. He was probably one of his first and one of the best students he had, with which Salam wrote about 30 articles. He was working in a Imperial College at some point, and then he moved to Australia. They started something called gauge technique in Schwinger-Dyson equations and its non-perturbative solution. Nobody before that had worked other than, at some point, Lattice started later on. Nobody had worked on non-perturbative solutions in quantum field theory. Everybody used to work on perturbation theory. So they were the first one looking for the possibility, what happens if the interaction between particles is large enough? How would we solve that? So they worked on quantum electrodynamics, assuming that its coupling was large and trying to find a solution for the interaction between electron and photons if the interactions were large. So this was the work done by them. Salam stopped working after writing 2 articles. Then Dilbergo worked on it with his students, who extended his work for QCD and also for the standard model. But then he stopped working on it as well till when I met him. I visited him and worked with him for 6 months, and we again took up this problem. Worked not exactly using the gauge technique, but we used different methods of solving a Dyson equation with Dilbergo. That's the closest connection that I had in terms of work with Dilbergo. Okay, so this was what Salam had done. I'll talk about 3 of these work. The other 2, which is supersymmetry and grand unification models, I'll not be talking about. I'm not an expert at it, and I don't have time either. So I will now come back to something simpler, which probably everybody would know. I hope most of these things will be known by people. I'll talk about 100 years history of particle physics from 1920 to about 2025, 105 years. But some of my friends are as old as I am are here. So for them, I'll go back a bit according to their times, and I'll start from about 1,500 years ago. So that will suit our ages more. Okay. So splitting the atom. So I'll start talking about atom, and I will talk about 2 particles. One is called pion, and one is called muon. Okay. Their story started a long time ago, more than 100 years ago. So they have crossed each other's path many times, although are very different kind of particles. But sometimes we have confused one with the other historically. Secondly, in some of the physical observables, when muon was supposed to make a huge discovery, pion just stole the thunder and just told that, look, once you had messed up with my discovery, now I'm going to mess up with you. So it's a story of these 2 particles, which spans over about 100, 105 years, and that's what I'll try to talk about and try to fit in where Salam's contribution came. Okay. So the idea of atom comes from some of the Greek philosopher many years ago. This guy, Democritus, he was the first one to say that atom is something which cannot be divided, and it's the smallest particle that we can see. He was right in his times, but his ideas were not based upon science; they were based upon philosophy. So you can't really say that as something scientific method. But then Dalton, who was a chemist and a physicist, English chemist and a physicist, he looked at the properties of different elements, and he more or less said the same thing. When I was giving lectures at NCTB last week, I was asking students that I will not only deliver the lectures, but I will leave homework to them. They should do it. And I hope that I can do the same thing, and they'll get back to me in a week or so. So Dalton said the same thing, that atoms are indestructible, and atoms of a given element are all the same in their characteristic. He, in fact, about 5 postulates. These are 2 of the 5. So I will ask students to find the other 3 postulates and tell me what they were. So that's when atoms knowledge became more scientific. Dalton was able to measure the weight of many of these elements. A lot of them were incorrect, but they were about the right ballpark. Then J.J. Thomson in 1897 most of you know, he is given the credit for the discovery of electron, his cathode ray experiment, in which electrons came out of the cathode, then they went through a hole which was kept in the anode, and then he adjusted external electric fields and magnetic fields, and that changes the path of an electron, which is a charged particle. And he was able to calculate even the charge to mass ratio of the electron. He was one of the first one to say that these were not really rays, but they were particles. Some people actually didn't trust him in the beginning. So he gave this kind of a model in which electrons are embedded between some positively charged background, because we know that atom was neutral. So if there are electrons negatively charged, there should be some positively charged background. Then one of his PhD students, who was an experimental physicist, Rutherford, carried out his experiments during these years to try to prove that his supervisor's model was correct. He only ended up saying that his supervisor was wrong. So he was the one to find the nucleus. This looks golden because he worked with gold nuclei, gold atoms. Okay, that's why I sometimes say, because nucleus is the first strongly interacting particles, I try to tell people that QCD is the theory of rich people. We work with gold, as compared to what Salam once mentioned. I'll come back to it when I'm talking about Salam about gravity. Okay, so he is given the credit to discover nucleus. The first nucleus he discovered through the experiments carried out of helium particles, which are the nuclei, alpha particles, which are the nuclei of helium atom, bombarded upon a layer of gold particles, and they discovered that the model is not like that. If all the mass of an atom was distributed equally inside the whole atom, the atom will become very diluted mass. Okay, and if it was very diluted, all of these particles, which had an energy of about 5 MeVs, they would go straight through, and none of that particle will ever return. So he did the experiment, and he said it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Because through a tissue paper, you suppose that all of them will go through, it will never be able to go back. But if you have that same tissue paper, and if you concentrate in a very small space, and if some particle happens to pass through that small space, it can get returned, because in that way is very massive. So that's what is happening. So all the mass of atom is in fact concentrated in a very, very small part, which he called the nucleus. And when some electrons or some helium particles passed close to that, they were deflected at a large angle. And that he concluded how much should be the mass of this nucleus. And then he, of course, continued to do experiment with other nuclei. So he gave some sort of a model. He had something in his mind, but he sent the results of his experiments to his fellow colleague, was Niels Bohr, who was also a student of J.J. Thomson. Niels Bohr was a theoretical physicist, so he said, look, that's what I'm getting. What do you think atom could look like? At that time, people knew that when an atom is heated up, what kind of spectrum of light it emits. Okay, so based upon the spectrum of hydrogen atom, that's what Niels Bohr did. Okay, so the electrons move around nucleus in fixed orbits. Not all orbits are possible because their angular momentum seem to be the integer multiple of what is called the Planck's constant, and that didn't allow all the orbits which could have been otherwise possible in classical mechanics. So here I gave this. So the electron, when an electron jumps from one orbit to the other, it gives off life. This n is light. N is equal to 2 is a particular orbit, because anything that comes to n is equal to 2 gives light, which is in the frequency range which our eyes can see. So it gives off the colors that we know of. So every atom has a particular signature. So when light comes from different other stars or galaxies, we can tell what they are made of, whether it's hydrogen, helium, and what concentration is there. So these experiments that Rutherford did lasted from 1906 to 1920. And 1920, he concluded, after working with a lot of elements, that the nucleus of hydrogen atom was the lightest, and he called it a proton. Okay? So that was the discovery of the proton that will be interested, and that was discovered in 1920. The story basically starts from 1920 when proton is discovered. The rest was just an introduction. Now, a few years later, in 1932, Chadwick discovered what is called the twin brother of the proton, which was later called neutron. So in these, so this is alpha particles. When they were bombarded on beryllium, there was some neutral radiation which came out. But those neutral radiation couldn't be photon because they were a lot more energetic. When they passed through something that had a lot of abundance of hydrogen and a lot of protons, they will kick protons out. And photons couldn't do it, light couldn't do it, gamma ray couldn't do it. In fact, doing experiments, scattering experiments, and the calculations of how much energy one particle can give to the other, he could calculate what was the mass of this particle, which was neutral, charge neutral, and that came out to be almost as the same mass as the proton, slightly more than neutron. Okay, and in fact, what they realized was the nuclear properties appeared completely independent of whether it was made of a proton or it was made of a neutron. Also, that their masses were the same. For example, these are two elements. These are the spectrum of the nuclei, not of the atoms, but the nuclei of these elements. Beryllium has 4 protons and 3 neutrons, whereas lithium has 4 neutrons and 3 protons, but their spectrum is almost basically the same. So it told us that the spectrum, strong spectrum, really doesn't depend very much on whether it's a neutron or a proton. That led Heisenberg in 1932, and later on, Wigner just improved his initial suggestion in 1937. They say that, in fact, a neutron or proton are 2 different representations of the same particle, which they call the nucleon. In fact, they associated what is called the isospin to neutron, just like an electron has spin, which is spin up and down. A nucleon can have isospin up and down. An isospin up would be a proton, an isospin down will be a neutron. So one of the things was, what holds the nucleus inside a nucleus together in a close proximity? This distance, the size of a nucleus, is of the order of 1 Fermi, which is 10 to the minus 15 meters. Now, the size of an atom is about 5 orders of magnitude bigger, which is 1 angstrom, 10 to the minus 10 meters. So there must be some very strong force holding them together. So this must be a short-range force in a small distance, and this must be extremely strong because they're combined together in a very small space. So that was the idea at that time. Now, in 1934, Yukawa proposed the idea that between this neutron and proton, there should be some particles exchange, just like electrons do. When electrons interact with each other, they interact through light. They exchange light between each other, and then they interact. Okay. And the reason it was short range was that pion was, unlike the light particles, had some mass. And he estimated that this mass should be around that 300 to 400 times the mass of an electron for it to have that short range. And that was the potential between them, unlike Coulomb's law, which you know that Coulomb's potential is 1 over r. So I think this is quite an interesting and nice analogy. If you have an electron can have an internal spin half. It can be pointing spin half or spin minus half, depending upon its direction of motion. So this spin half up electron can go to a spin down electron when it absorbs a photon, which has its own spin pointing in the down direction. So it imparts it in the direction, and this can get converted into this. So Yukawa thought that in the same way, a spin half nucleon, which is a proton, can convert into a neutron through the exchange of a particle which has isospin 1 instead of a spin 1, which is a photon. Right? So those were called pions. And we now know that, yes, there is an isospin 1 particle pion, which has 3 different kinds of isospin, and that is either a pi plus, pi 0, or pi minus. Okay? And therefore, what happens inside a nucleus is there is a proton. It emits a pi plus, and that pi plus is eventually absorbed by a neutron. So neutron becomes a proton, and the proton becomes a neutron. So it's always they are changing their identity. A neutron getting converted to a proton, vice versa, back to the exchange of pion. That is one of the reasons that neutron doesn't decay. If neutron is alone, I think its half-life is about 12 minutes, something like that. So it will eventually decay. But inside a nucleus, it's a stable particle because it doesn't really remain a neutron. It's a neutron, but much before it will decay, it will become a proton, then back to neutron, and therefore it gives a stable nucleus. Right? So this pion is something very interesting, even for modern physics. In fact, the first project that Abdus Salam received when he went to do his PhD was that this theory of nuclear, neutron, proton, and pion was not a renormalized theory, and he worked on that. That was a wrong project with wrong conclusions because it's still not renormalized. So it shouldn't have been tried to be renormalized because it's not an interaction between fundamental particles. But anyway, that's history now. So that particle was predicted in 1934, and pion, this will become very important, this storyline. It was supposedly discovered in 1936, 2 years later, by Anderson and Naddermeyer. This was the same guy who discovered positron about 4 years before. And they called it, some people call it meson, other people called it, what was it called? Upon. I don't know why that name, but Neil Bohr and some other people call it that part. It only came to their notice afterward that this couldn't be a pion, because it, in fact, what the particles that they discovered never interact with the neutron or a proton. So it couldn't be the same particle because pion is supposed to interact with neutron and proton. So they called it a muon. In fact, one of the guys, one of the famous scientists, got a Nobel Prize himself, I think, on magnetic properties of atomic fields, Rabi. When he discovered that it was some other particle, he said, who had ordered muon? Why does it even exist? So for that, I want to tell you that now, currently, we know that there are many fundamental particles. They are divided into these parts, leptons and quarks. There are 6 types of quarks and 6 types of leptons. There are electron, muon, tau, these neutrinos. These are leptons, these are quarks. In fact, there is a stair here. Here, neutrinos are lying on the lowest stair, which says weak interactions. These are the particles which interact quickly. Then there are electron, muon, and tau. On this stair later is electromagnetism. They interact with each other through electromagnetic interactions, or weak interactions. And then there are quarks, which participate in all interactions. So the story at that point was that we knew what were protons with neutrons, and pions had been predicted. But we know that only up and down parts make these pions and protons. A pion is made of a U quark and an anti-down. A proton is made of 2 up quarks and 1 down quark, and a neutron is made of 2 down and 1 up. So the whole atom is basically only made of these 3 particles: up quark, down quark, and electrons. Electrons are outside, and protons and neutrons are inside. So these are the only 3 particles needed to explain nuclear physics, atomic physics, molecular physics, and everything we see in the universe. Why the hell there is a muon? What is the role of this particle? Why does it exist if it is not even found? Which we found in cosmic rays. So now we know that all these particles exist, and in 1960s, the theory of these particles, of all these particles, and how they interact through electromagnetic interactions, weak interactions, and in some way also strong interactions, was given by Glashow, Weinberg, and Salam. Okay. So even from 1960s to now, we know that this model works very well. It's something like, at some point, Newton's laws work. So there is nothing new that we need to know. That theory is infallible, and I personally am very happy about it. There are many other particle physics who would love this theory to be proven wrong, because if not, we will not get the jobs. If everything has been done, there's nothing else that we can do. So, there are three kind of schools on that. So that is one of the works of Salam. So now I will go out of muon and proton and pion. I will not even tell what happened to the pion for some time. Now the muon has discovered. Let's talk a little bit about muon. A muon has what is called a magnetic moment. Those people who are engineers, they know that when you have for example, a current loop, it can interact with the external magnetic field and it has magnetic moment. And the more you have current, for example, the more that external magnetic field can produce a torque in it, and therefore the current times the area that it covers the current loop is called what is called the magnetic moment. The same thing happens for an electron. It has an internal spin. A muon has an internal spin, so it's like an angular momentum, and therefore it has a magnetic moment, and it interacts with an external magnetic field. Okay? So that is the magnetic field of fundamental particles which have charge, which have mass. Now Dirac, that I have special fondness for, that I've told a few minutes ago, Dirac was the supervisor of my supervisor. So I have a lot of fondness for Dirac's work. Dirac was the first one through the Dirac equation, predict through the equation that the strength of that magnetic moment for an electron muon given by this gyromagnetic ratio is equal to this value G. People knew that it was 2, but it never came out of the equation before. You can search it in Schrodinger's equation through what is, through how Pauli had done it. But this Dirac equation had in itself, it was a prediction of G equal to 2 for an electron muon. But then we know that in fact, it's not exactly 2. It's slightly different from 2. Okay? And there is a whole story associated with it, which is very exciting, but I don't have time to go through that. Now that small difference from 2 enabled us to try to understand quantum electrodynamics, how it works. Okay? For about 15, 16 years, people didn't know, from the birth of quantum electrodynamics around 1928 to about 1945, around 20 years, people could do only rough calculations. And those rough calculations were enough because those were the ones which were measured in experiment. There was nothing more needed. But in 1947, when Lamb did measurements and told us that experiment had become much more precise than theory, then the pair got together to see if we have to fix that problem somehow. So what is called the birth of new quantum electrodynamics, which I can call the renormalized quantum electrodynamics, the real theory that we have. It was established in 1943 by Tomonaga and 1947-48 by Schwinger and Feynman. These were the times of the Second World War. So this Japanese guy who had worked this much earlier, that work had not reached the other part of the Atlantic Ocean till 5 years later. So anyway, I think they all had done this work independently. And once that was invented, people could calculate what was the difference from experiment. And that is called the anomalous magnetic moment, how much it is different from the prediction of Dirac. That first calculation was done by Schwinger in 1949, which the first correction was calculated, and that's alpha over 2 pi was around 0.1166. Okay, now that now serves as the test of the standard model of Salam, Weinberg, and Glashow. Now people can measure it with extreme accuracy in the experiment, and you can also predict it by using the standard model. The precision is up to about 10 significant digits after the decimal point. And the same is the level of prediction. So if there is a slight difference between the two, you can tell that the theory is wrong or the theory is right. And that particle muon sits at a very sweet spot. It is sensitive to if theory needs something else, and it also provides us possibility to carry out experiment on it. Okay? This is more sensitive to new physics or different kind of physics, but we can't do experiment on it because it decays very fast and doesn't give us enough time to work on it. Okay? This stays stable, but it's not very sensitive to new physics. So muon is the right particle on which we should work. So people forgot about in that sense, you can forget about Pion for a while because muon has taken all the importance of the scene. And then, this is for particle physicists. How do you calculate this G minus 2? It is this form factor, which is called the Pauli form factor. And so these particles, which are muon, these are on shell, and this photon has this momentum q squared when it is equal to 0. This is exactly actually G minus. Okay? So once you can calculate or measure or predict it, you can tell if the theory is correct. So the standard model, there were landmark articles written in 1967 by Weinberg and 1968 by Salam. So I was telling you about quantum electrodynamics, electromagnetic interactions. When they were proved that they were renormalizable, means that they were able to do exact predictions, then it became a very workable theory. But when they gave standard model, Weinberg didn't know that this standard model was also renormalizable or not. Was it a meaningless theory? Only could meaningless, not meaningless, that could make predictions only at the tree level or also at the loop level. So there was a conjecture. It says it is probably renormalizable, but then who knows? Because there was a shifting of fields because of the Higgs condensate. And in that shifting of fields, Weinberg didn't know that it still remained renormalizable or not. And then in Salam's article, which was written in 1968, you can say that both forces affect equally well on metal leptons, but also on hadrons. Hadrons are like pions and protons and neutrons, but that was just left like that. People didn't go into detail of how that works. It was a theory of leptons, but also affected hadrons, including protons, pions, and kaons. So when you, using the standard model, calculate the magnetic moment of the muon, what happens is that that magnetic moment gets affected by the production of the pion. Okay, so muon, which has messed up with the prediction of pion and got discovered instead of the pion, its property could not be measured without really understanding the pion. So it got entangled, the whole thing. So I think that is the point. Then I will first talk about what the problem is, and then we will talk about the story, pion story, because we left out the story. So this is the standard model given by Weinberg et Salam in 1967. Nobody cared about that model for next 3 or 4 years because mostly because it was not proved to be renormalizable. Okay. Then these guys, Weltman and Tooft. Weltman was a supervisor who basically didn't do any work. It was a PhD student who did the work, but both of them took the credit. Tooft and Weltman, they proved in 1972 in 2 articles that the theory of standard model was renormalizable. So before that, they had received only about 3 citations by other people, but after it was discovered, within a few months, it had thousands of citations, and everybody started talking about standard model. So that the standard model you can use and measure many things, calculate many things, which you can also measure and experiment. This is one of the most important things. This is probably one of the most precise measurement of any quantity in physics that you can ever do. And you can also make the prediction from the very fundamental principle from the standard model. Okay? So these corrections come from various interactions, quantum electrodynamics, from weak interactions, from strong interactions where pion, proton, and neutron play an important role. And those strong interactions can be divided into 2 parts. One is called the hadron vacuum polarization, and the other is hadron light scattering. If some of you don't know, that's not a big deal. The only thing I want to tell you is that in 2020, there were 120 physicists who got together to write what's happening in the field. I happen to be one of those 120, but that's not a big deal. 120 are a lot. What they tried to do was to try to see what's the status of this. What the theory predicts, does the experiment tell us the same thing or not? So the final conclusion in that setup was no. The standard model prediction lies somewhere here, and the experiment tells us the results for that G-2 is somewhere there. Okay. This sigma, I don't know, somebody else can tell it, but 4.2 sigma means that it's almost certain that there's something new needed. That standard model is not enough or not correct. So, to this fine detail. In fact, that year in the Fermi Laboratory near Chicago, in their web page, there was this release. They said, first results from Fermi Labs Muon G-2 experiment strengthen evidence for new physics, saying the standard model is not sufficient. Okay. That was based upon these results, which compared theory with experiment. Okay. Now, I'll stop that story in 2020 for a while, and I'll come back to what is a pion. Okay. This is actually my field of research, a pion. And I will talk about what are the strong interactions inside a proton and a neutron. We have now told that protons and neutrons are made of quarks, and inside those quarks, between those quarks, are strong interactions. You see the way electrons and protons interact with each other through emission and absorption of light. Quarks interact with each other through emission and absorption of gluons. Okay, so that theory of QCD interaction was given in 1973, and these 3 gentlemen received the Nobel Prize much later in 2005. So the idea is that when two quarks are very close to each other, don't feel each other's presence, which is very unlike the electrons. But when they start moving away from each other, the interaction between them increases a lot. Okay? So when they're very close, they exhibit something called, I don't know, behave like free particles, which is called asymptotic freedom. So that theory was given by these. When we go back to what are the particles which participate in these kind of interactions, then you know that Pion was predicted in 1934. Then there are other particles, kaons, lambdas, sigmas, and by about 1960s, there are dozens and dozens of such particles which interact with each other through this new kind of strong interaction. Okay? In fact, I had told you that Yukawa had predicted in 1934 the pion. In 1936, they detected muon, not the pion. But the pion was detected by Cecil Powell in 1948. When he detected in 1948, immediately 1 year later, Yukawa won the Nobel Prize in 1949 for its prediction. In 1950, this experimentalist himself got the Nobel Prize for devising new experimental techniques for this discovery. And later in 1960? 1960, Nambu, in a way, incorporated this pion degrees of freedom to explain what is called chiral symmetry breaking and why the photon is so heavy instead of being light and like electron. Okay? And he got a Nobel Prize in the work that he had done in 1960 in 2008. He shared the Nobel Prize with whom did he share? With Mascara and who else was it? Kobayashi? No. I don't know.
Yeah, Kobayashi.
Kobayashi,
yeah.
And
they left out Kabibo.
Yeah, they had done it with Kabibo angle, and Namu had won on chiral symmetry breaking. So they shared the Nobel Prize. And in fact, what happened was that people had detected muon and confused it with a pion because they were not so high with the cosmic rays, because I think somebody here does cosmic rays. Anyway, so if you go higher up on the mountains, then the first thing that comes from cosmic rays are the pions. But then they decay into the muons, and what was first detected was the muon. But if you do your experiment at a higher place, then you will find the pions. So the pions were discovered about 10, 12 years later. And I was talking about the strange kind of chiral symmetry, and those people, who are physicists, particle physicists, who know what I'm talking about. An electron or a quark up and down, they can have what is called the left parallelity and the right parallelity. And if they're massless quarks, if they have no mass, it is something like the projection of spin in the direction of their motion. If a quark is moving in this direction, its spin is also pointing in this direction. That means it has right chirality, and if it's another section, it's left chirality, or the other way around, something like that.
हो गया
Okay. Oh, Alex is there as well. That's nice.
Hi Adnan.
Hi Alex, how are you doing?
Very
What time
fine.
is it?
I'm enjoying your talk. Continue,
Okay.
please continue.
They're going to mute you. Okay. So there are right chiral quarks and there are left chirality quarks. So that equations of motions have certain symmetry of the fundamental particle. This is one of the very interesting symmetry, which is called left-right symmetry. If the particles are completely massless, which have no mass, then there is special kind of transformations for left parallel quarks and right parallel quarks. They don't mix with each other. They live in separate worlds, and they have their own transformations, and that is a symmetry of these interactions. Okay? But when they acquire mass, they mess up the things a little bit. And that was a thing which was happening with Glashow's theory in 1961. He didn't want to put the masses because that was messing up the renormalizability of the theory, and he didn't know how to get rid of it. So assume that every particle was mass. And that was a theory given by Glashow in 1961. When you put the masses for these particles, this left parallel quarks start talking to the right parallel quarks, that symmetry is broken. And that symmetry is broken because of the strong interactions. Strong interactions mean that if you're living inside a proton, the interactions of QCD change the entire vacuum inside a proton, because the energy fluctuations or even of the vacuum inside a proton are huge. There are virtual particles created and destroyed all the time, and that is what is shown. This is the current. This is the current density of gluons in about the distance of the size of 2 or 3 protons, like 2 or 3 fermis. Right? And this tells you how the vacuum of a proton or neutron looks like. Okay, it's very vibrant, so much so that it changes the internal, the whole structure of the vacuum itself. Vacuum doesn't remain a vacuum as such. So what happens to the quarks which are inside a proton? When they are very close to each other at distances of 10 to minus, I don't know, minus 17 meters, they're almost free. But when they try to go towards the edge of a proton or go away from each other, they become more and more massive. They become hugely massive, and because of the color confinement, they can't leave the proton. Okay? So that happens due to vacuum fluctuation and what is called the dynamical generation of mass. And these particles are produced, many people just call them Goldstone bosons. They're produced, and that their mass depends upon the property of the vacuum. If vacuum becomes non-trivial, then these particles acquire their existence. And they're massless, but if initially up and down quarks have some masses, the Lagrangian, then they become slightly massive, but they still remain as the lightest hadrons, lightest particles which interact through QCD interactions. Okay? So I want to just step back a little bit, that this was one of the first articles, I think, produced by Nabu in 1960. He didn't know about the existence of quarks, but he knew that there should be some fundamental field which breaks chiral symmetry, and that breaking of chiral symmetry gives a lot of mass to the proton. How does that exactly work? I don't know. But he thought that pion was in fact the production of the breaking of that symmetry. Otherwise, pion wouldn't exist. So that was one of the works that was done by Nabu. But then next year, there was another work in which Abdus Salam was involved. It was Goldstone, Salam, and Stephen Weinberg. So from yesterday on, I've decided that I will not call them Goldstone bosons. I will call them Nabu, Goldstone, Salam, Weinberg bosons. That's a long name, but I think it's worth it. You have to give the credit to the people who worked on it. And in fact, this article was the first article which gave a formal proof that these Goldstone bosons should exist. It no longer was a conjecture, but it was proven by Salam, Weinberg, and Goldstone. Right? So I think that was important, and that is where pion starts an important role. Right? So that's the story of the pion, and there was a story of the muon. Now, the last part, I will come to how that story mixes up. I was telling you about this calculation and the experimental measurement of what is called the muon anomalous magnetic moment. Okay. So in 2020, when everybody was telling that there's something wrong in the Standard Model, okay, one of the things that causes the big mess is the calculation of this diagram. Okay, and this is just the same diagram at a higher level, higher loop level. So what happens is that this calculation from the Standard Model has a lot of uncertainty. People didn't know exactly how to calculate it, but they thought they were doing the right thing. And based upon that computation, I showed you this. The result of the calculation of this diagrams give you the anomalous magnetic moment of the muon, which is this prediction. But if it had to agree with the experiment, this calculation, this result should have been sitting somewhere here. If it's not sitting here, there is something wrong with the Standard Model. Now, there could be two things. One could be that there is something other than the Standard Model. There's some new particles that we haven't discovered yet. There are new interactions that we don't know yet, or we messed up the calculation. And which calculation messes it up more? It is the one which has a pion. Because pion contributes more than 70% to this calculation. And in fact, what was discovered was that that's exactly what it is. In fact, there were some people who were telling us even before we wrote the white paper that no, we don't think that lattice calculations have been done correct. In fact, when I went to Keynes at the end of 2024 in December, this BMW collaboration of lattice, one of their representatives came and he gave them the talk and he said that their collaboration have been doing this calculation since 2017. Their first result for this, which is within the standard model prediction. Then they made a more accurate prediction in 2020, still very close to standard model results. And 2024, their result sits right where the standard model measurement is. Their prediction was that. But in the white paper, people took the average, when I said people, I was also involved. When you take the average of all of this, the average stood somewhere here, which they were told that there was some discrepancy between what standard model was telling and what experiment was measuring. But with time, things have changed. So I don't know who was asking me. I think you were talking about what were the possible sources of error. Because when lattice does this calculation on a computer, which is discretized in space and time, they have certain finite length of time and finite volume. That was improved. Statistical errors were improved. Physical point where the point mass is, that was improved. Continuum limit was taken better. And then also they took into account the isosceles symmetry breaking effect. So all of this was improved. And once that was improved, then instead of the theoretical prediction being here, first was lying somewhere here. And with the improved results, it was lying here, right on top where the experimental results were available. So they were the first one to tell that there is no discrepancy between theory and experiment, at least not today. So the standard model of Salam, Weinberg, and Glashow is perfectly intact. Now I have to do my personal publicity as well. Why have I come here to publicize what lattice does? Okay, so just put up with me and I'll put up a couple of transparencies which is related to my work. So lattice is one way of calculating QCD effects or the strong interaction effects in the standard model. But of course, we can't rely on one single method. So I was learning as a PhD student another method with my supervisor, Michael Pennington. And when we were writing our first article, I remember he came to my office and I said, look, Salam worked on it. And he gave me Salam's article to read. And this was the first article that Salam had written on the same subject that I was getting prepared during my doctoral. Salam and Dilbergo. They worked on something called the continuous treatment of QCD instead of a discrete treatment of QCD, which is done in lattice QCD. So I learned that with him, and then Salam only wrote 2 articles with Bob Dilbergo, and then Bob went on to keep writing articles with his students and other people in 70s and early 80s. But then I went and did my first visit with him in 1999, and I think I was very lucky to have, although not worked directly with Salam, but I worked with one of his students who had written 30 articles with Salam. So we wrote about 4 to 6 articles with Bob Dilbergo on the same field, looking for non-productive solutions in quantum electrodynamics. Okay, but not through gauge technique, but a different kind of truncation schemes, the different methods of observing the symmetries of that. So that's where I learned this. And after that, I went on to study much later, I don't know, about 15 years later, internal properties of the pion. I was not interested in the muon at that time. I just wanted to know how the pion was internally, because that is important to understand strong interactions. But then we realized that that pion, through different kind of interactions, is used to calculate the muon anomalous magnetic moment. Okay. For example, this pion, which is pi 0, can decay into 2 photons, and that interaction is important in calculating the G minus for the muon. So what we had computed the transition, we used that to see how much was the effect of this in the G minus 2 of the muon. Okay. So we computed this result in this article written in 2020, and we can compare the dispersive method or lattice gave almost the same result. Well, you can't this because this is only pi 0 pole. It comes from lattice, which is 59.7. We have 61.4. This is bigger error because it's small mass particles, and dispersive method are closer to what we find. Anyway, all are within the same experimental error. So we realized that with our method, we could produce a result which had more or less the same precision as other methods. And then this pi plus or pi minus, which are charged particles, their elastic form factor gives another contribution. And later in an article in 2022, we could also compute that. And that also was in the same ballpark as the other method. Okay? But what we could do was that people had never calculated the contribution of two other mesons that we had managed to do. And then we also included here some excited mesons, and that work was completed in 2025 last year. Anyway, so that was one story. But we never computed that effect, which really explains the G minus Q anomaly. So my postdoc who had done this work started working on it 3 years ago. But it's only after about 2.5 years that he managed to complete his computer program, computer code, and started sending the result. Okay. So this was the latest result, which in, we wrote an update of that white paper in 2025, in which we report that the experimental result is exactly where the standard model tells us that it should be. Okay? But only about 1 month ago, my postdoc also sent me his first results using Schwinger-Dyson equation method, using continuum QCD, and that is also almost like with the standard model result. The only thing we haven't taken into account here is what is called the isospin symmetry breaking effect. But he has done it, but he's asking me not to show it to anyone because it is still preliminary and he's not confident about it. But he knows that once you take into account isospin symmetry breaking, which means the difference of masses between up and down quarks, this results also sits on top of the standard model. Okay, so which means that in a way, what we can say is that the Schwinger-Dyson equation studies which we carry out yield the results for the anomalous magnetic moment of the muon, which are compatible with the results produced by lattice QCD, providing finally a converging understanding of standard model predictions so that we can compare predictions from different sources with experimental results, and which puts everything into perspective. So this is the final word. This is the finished report which we wrote in 2025. And so there again, I've only shown here 20 people, there are 20,000 people more. No, there are about 100 people in total. And it says what the conclusion is, that it implies that there is no tension between the standard model and experiment at the current level, at least for this conclusion. The only thing we had to do is to understand how the calculations were done better than before. I will give it a pause of a few minutes if any of you have any questions, because I still have something to show about Salam, which is not to do with this. Any questions?
Should we treat it as good news or bad news?
It's satisfactory news in some sense, I would say. In the sense that you see there are many models which go beyond the standard model. In fact, Salam himself worked on models thinking what if standard model was not right, then could be supersymmetry, could be unification models. But I would take as a good point in the sense that when Lamb had done the same thing in QED, we had to understand quantum electrodynamics better. But I think the time has come when we have to understand strong interactions better and to be able to calculate them. There is a new experiment in Japan which will start taking data in 2028, and that is going to give experimental results which is even going to be 1/4 more accurate, 4 times more accurate than these results. But we don't have theoretical predictions as precise as that. So somebody has to come up with new ideas to solve QCD in a more exact manner. Because if we don't understand QCD, then you can't say that standard model is wrong or right. Okay? So I think it's a challenge like the time we had in 1947 for quantum electrodynamics. But now at least people are making improved calculations both through continuum and lattice. Any other question?
About the results from the lattice calculation, are they from standard QCD?
No. They have all the standard model.
With the ground for close one, of course.
Okay, so this was Salam's contribution, which came in three directions. I think the standard model itself, then his prediction for the pion in terms of the article that he wrote with Glashow and Weinberg, and secondly, he was the first one to solve Schwinger-Dyson equations, and that set the stage for solving QCD in continuum to make such prediction. So I think in that way, I am indebted to him for all these three things, that he was the one who started along with some other people. Okay? And the other things, there are more experts who can talk about unification models or supersymmetry. I don't know much about that. What I will do is now addressing myself more to the students, okay, who are sitting in front of me and who are the future. I might be the past of particle physics. You are the future of not only particle physics, but physics, engineering, whatever. One of the sayings that I really like by Abdus Salam in his book Ideas and Reality is that scientific thought is the common heritage of all men. It doesn't really matter where you sit, whether you're sitting in Chang or you're sitting in a remote village in Mexico, or you are somewhere else, sitting in some country of the first world. That knowledge belongs to everyone, and everybody can contribute. If Salam could do it, everybody could do it. We shouldn't go just from this lecture with a sense of pride in Salam, but with a sense of responsibility. Okay, because we all have the responsibility to do it. We can't just keep taking pride in what happened 50 years ago, but we should go home with a sense of responsibility to do the same thing, all of us. So this is, I like quite a bit. And in fact, I have to tell you the story. Many of you, this story have heard from me 100 times, but those who haven't listened to it, they can. So Salam was the one who, unified electromagnetic and weak interactions. But he tells that his first introduction to fundamental forces was when he went to his classroom in Chang. And his teacher came and he said, guys, there are three kinds of fundamental forces. One is nuclear force that exists only in USA and Europe. Then there is electricity, which is only in big cities like Karachi and Lahore. Here in Chang, we only have gravity. So he said that was his first introduction to fundamental forces. In Pakistan, things have become worse because now even in big cities, we don't have it. So let's hope things will improve. But even with this first introduction, he came out to become a scientist who worked on the forefront of fundamental interactions and gave the final say in the standard model of particle physics, which unifies these interactions and gives a model which still stands for 2025. This is not the only observable. It's generally true for all other observables that have been measured. But just because G-2 is special, because it's very precise, I focus my attention on that particular observable. So Salam understood that talent exists everywhere, but opportunity does not. Okay. So he went on to create International Center for Theoretical Physics in Trieste, Italy. And he created pathways for scientists from developing countries to participate in frontier research. Okay? And after his death, the Italian government has now calls it Abdus Salam Institute, International Center for Theoretical. Now that, in fact, continued what he did in that field. Now their partner institute of ICDP, which also provide opportunities for people from third world countries, do not have the same opportunities sitting in their places if there were no centers like that. So there is ICDP's South American Institute for Fundamental Research in Sao Paulo in Brazil. There is this East African Institute in Rwanda. Then there is ICDP Asia Pacific. And what I wanted to talk a little bit about was Mesoamerican Institute of Sciences in Chiapas in Mexico, because I worked in Mexico for quite a while, and I had some sort of link with that, and I was quite proudly, participating in these because I knew that it was a partner institute of ICDP of Salam. Now that Mesoamerican Center for Theoretical Physics is built in Mexico in the southeast eastern part of the country in the state of Chiapas, in the city called Tuxtla Gutiérrez. Okay? It's now exists for many years. And it was built to be able to cater to the needs of Central American countries and the countries in in Jamaica and other places nearby. So at that time, Abdul Salam had died. And if I'm not wrong, when this center was proposed, it was Fernando Quevedo, who was the director of that institute. And his interest was to create the center near the southern border of Mexico was because he himself was born in Honduras, which is a Central American country, and then he moved to Guatemala, and he had a Guatemalan nationality. So that is something that I have slightly in common because my wife was from Guatemala, and she used to tell me that there was no institution in Central America who would do research in fundamental physics. And if I do, why wouldn't I take some of it? So we had no other means, but when MCTP was built, I was able to talk to this first director of MCTP, Arnolfo Cepeda, one of the most wonderful scientists and people that I knew in Mexico. One of the interesting thing about him was that, that he used to drink a lot. Okay, so I know that when I started talking to him about starting some research in Central American countries, we were sitting in the VIP lounge of Aeromexico. He took me there because he could have a lot of tequila, get drunk or tequila. And I was talking to him, I said, look, I think that we can start through the MCTP and ICTP helps some schools in fundamental physics in Central America. And he said, can you bring tequila from tequila shop? So, and then after tequila, he said, why don't you apply for it? I said, okay, I will apply for it. He said, no, do it now. You have your computer, open it up and send me the application. He said, do you have any proposal more or less in mind? We had already started one in Mexico, and I changed the word Mexico to Guatemala, did a few changes, and just sent him in 10 minutes time. He's sitting in front of him, going for his fourth tequila. And then he sent me the reply that he has accepted it and he will fund it. And then he immediately sent an email to 7 different Central American countries and through all the funding agencies there, and some of them replied. And it was already decided that in August 2015, we will have the first Central American school in Guatemala. Okay, it was all arranged. And by the time it was arranged, he missed his flight because he didn't take into account the time and he didn't think how drunk he was. So he decided to stay overnight in Mexico City. I took my flight and went to where I had to go. But then in 2015, the first Central American Fundamental School of Physics was organized. After that, in fact, those schools were organized in Honduras, in El Salvador, in Costa Rica, about 6 or 7 of them. We never could find anyone to organize it in Belize or Nicaragua or Panama. But then at least it was a good start, and I feel very happy that MCTP through ICTP was still providing funding. Even when I go to Brazil, I went there 2 years ago, and when I reached there, I said, "Oh, we will pay for your stay and your food," and that came from the institute that was in Italy, founded by Abdul Salam. So wherever I go, there's some connection with Abdul Salam, either in terms of particle physics or in terms of his efforts that he did for the third world country. And I take a lot of pride. And more than that, I do take a sense of responsibility that we owe it to him, and we have to continue, some of us, doing that. So final message to students: as undergraduate professor, you're privileged holders of access to advanced knowledge. All of you who are sitting here are very special, and you have a lot of privilege. And as you know, with privilege comes responsibility. And you should feel responsible of what you're going to do in research. And not only that, how are you going to help society and take that knowledge not only so at a personal level, you should aim for global excellence and then apply it to both local and global challenges, just like Salam did. It's not an easy task, but we have to do it. A lot more important for what as professionals we can take from society is what we can give to society. And that's what Salam also always believed in. And that's where I go. Thank you.
All right, so there should be many questions now.
You reserve the right to ask question. I reserve the right not to answer.
No, we're going to force you to answer. Yes,
Anything
please.
that you want to, I don't know many things. There's some things that I can probably answer if you have. These girls have been asking me questions yesterday as well. So
Yeah, that's fine. Yeah. Anyway,
anything.
come on.
Or even you don't have to ask question. Anything you want to say or contribute, please feel free to add whatever you have to add or subtract.
So can I add a little tidbit?
Yeah, please do it.
So you were talking about renormalization and how Salam got his first problem, and that was the wrong problem to work on. Turns out the first problem that made him famous was working on renormalization itself, but it was renormalization of QED.
This zero, yeah.
So it was on calculating the overlapping divergences.
Yeah, for scalar QED, I think he did that.
I think that was his PhD thesis.
No, it was after his PhD. Or was it part of it? So maybe part of it, the PhD thesis. I don't know. That's
those overlapping divergences that caused a lot of problem in my life.
Okay. Yeah, very good. Yes, you had something to say. Yes.
I think my third approach to QCD, so we have the lattice, you have the Schwinger dissect equations.
Yeah, there are a lot of approaches. There are a lot of. I would say that these things are also, although some of these people, both the Schwinger dissect camp and the lattice camp, try to tell people that it is real first principles QCD. I think none of that is first principles QCD. It's all modeling in some way the strong interactions. Some can do it better than others. And for some particles, we can do it better than others. Then there are other modeling that exist. You have effective quark models. Then there is what is called the large N approximation. So some of the static properties of hadrons can be quite well calculated. If you assume that your perturbative parameter is not the running coupling, but it's 1 over n, it's either 1 over nc or 1 over nf, number of colors, number of layers, and then you take the large nc limit. So some of these, at least in tree level or bundle calculations, you can do called scalar perturbation theory. But all of those can see glimpses of not everything. So some of those models are good for some things and not for other things.
So there was this program of amplitudes, I think, started with what's his name, Nima Arkani Hamid. Did they get into QCD or new way of computing amplitudes and stuff like that?
Anybody else
They were.
can say anything better on that, or I just take my guess? Does anyone? Do you know better on?
I don't. No. I'm just asking because I just remember attending. I just remember attending a school a long time ago where somebody gave a couple of lectures on those amplitudes, and this was way back in 2013. I don't remember anything from it. I'm just asking.
If I'm not wrong, most of these amplitudes can be calculated in the perturbative regime, and yes, that technically they become much easier to do. Higher level calculations can be done much easier with those methods. Then there are those, how do you call them? There's conformal mappings for holographic QCD.
Okay, yeah.
But I think.
But then holographic, that's just specialized theories which just make the coupling weak in one limit, and so it just just becomes.
So what you can say that strong coupling QCD is identical to some other theory which weak coupling.
Yeah.
But that how do you say that mapping? If I think is exact only for the massless limit, and
it's an exact mapping only in the case of something like n equals 4c.
Exactly.
It's a very
something that is not really
specialized. Yeah. No, but the amplitude program that I'm talking about is a different.
That's different.
Yeah.
That is exact.
Yeah. That's
That,
slightly
that,
different.
that does give you calculational efficiency, but then there are others as well. What is called this proper time method of solving integrals through what is called the second order description of quantum electrodynamics with some fictitious fields. And those people can calculate one loop, higher external particles amplitude much more easily. There are techniques which help you, but I think that the non-perturbative methods still have only model, like tidal perturbation, effective quark model, large NC limit models, and more tangible than that.
Okay. More questions, comments? Yes, at the back.
You were talking about the bound state of quarks, where, for example, a proton, and you said that, if I got this correct, that when they're close together and you don't feel you want an exchange, but as they go far, they start feeling it. How do we measure that? Like, how do we know?
We don't measure that. We don't measure that. I don't know how to answer that. Let me try to answer. See, when Rutherford had discovered nucleus, he actually did not isolate it. What he did was just to calculate the spectrum. And the knowledge he said, because he told us that time. Now, in 1960s, very similar kind of experiments were done at MIT side. But that was not done by alpha particles, that was done by electrons. And instead of having energy of about 5 MeV developed, the electron energy for 20 G. So they could be silently. Quarks were never seen, they are still not seen. They don't have any real tangible identity in that sense. But again, difference cross sections were calculated, and they agreed with the calculation only if we assume that they were free scattering centers, and at large energies, you could even tell what were the masses of them. If you give them a mass of 5, 6, it's not exact, for a certain range, you will explain your question results to what getting there. Now that thing continue. You can do experiments in different ranges. You can have, for example, when Gellman gave a spark model, that was the first model. So he had to assume such mass relation between ions and neutrons, and that could only be explained if he assumed that the effective quark mass is a few hundred. But those are not the ones which are seen in the experiment, which are in high energy. They tell us that those masses should be MeVs. So you know that whatever masses, when the distances are small, or of the order of few MeVs, but if you have to scan the physics at large distances, you can't use the same masses because effectively they become. But there are ways of calculating it. But the problem with quarks is that yes, you cannot isolate that. It's just indirect. Makes me an indirect.
Okay, I saw a hand in this general direction. Yes, go ahead.
इसलिए करनी थी आपने बताया कि yes के अंदर तो ड्रोन जो है आपने बताया कि उसका ड्राइव फ्लाइट ठीक है तो मतलब वो अगर प्रोटॉन में चेंज हो रहा है वो तो चलिए ठीक है प्रोटॉन तो स्टेबल है वो प्रोटॉन में चेंज हो रहा है.
That's the very universal part. The thing is, proton, in fact, I didn't tell you because I thought it was probably not so relevant. In fact, kinematically, it is not allowed to be real particles because proton is lighter than neutron. But virtual particles can have masses. You know what virtual particles are not, because they're not real particles, so their characteristics are not exactly the same as the real particle. So proton and neutron, so if neutron goes, it converts into a proton and emits a pion, vice versa. Because they're virtual particles, their masses can vary. That means they're 4 momentum squared, not necessarily mass of the particle. So yeah, a proton is positively charged, it makes a pi plus. So the charge is carried by the particles. So the neutral particle is neutron.
न्यूट्रॉन स्टेबल नहीं है वो तो प्रोटॉन में चेंज
It's not the matter of stability. It's the matter of exchange particle, virtual particle. They keep it. It's not because neutron is not stable that this is happening. Even if it were neutron was stable, the same thing would still happen. So this is just strong interactions. Electrons are stable, but electron up must to electron down by taking a photon. Not that electron is unstable. Because the QD interaction.
ये न्यूट्रिनो ऑसिलेशंस मतलब
That's a different story.
यहाँ पे जो हो रहा है कि वो प्रोटॉन न्यूट्रॉन में चेंज हो रहा है न्यूट्रॉन प्रोटॉन में वहाँ पे भी फ्लेवर चेंज हो
It's the same isospin, they're not changing it there. The isospin is still half.
Okay. Yes, Tasna.
To what extent is this statement correct that proton and neutron are actually just two states of one entity? Because some
You mean, how exactly is isospin symmetry?
Oh, correct, are you saying that? Because some people did calculations using electrodynamics, quantum electrodynamics. They say that the difference between the Z boson and W boson is about 10 GeV maybe. And this is the electromagnetic interaction.
I actually don't know exactly what is that. But if you come to proton and neutron, I can't say about W and Z. I think that just comes from the Weinberg mix that is available. But proton and neutron would be exactly corresponding to the same nucleon if they had exactly the same mass. But they don't have the exact same mass. Neutron is very slightly more massive than the proton. So in fact, that conjecture that it is the same nucleon is only true for strong interactions.
As long as we're completely ignoring QD.
As long as they're ignoring to quantum electrodynamics, and also if you're ignoring the Lagrangian mass of up and down band. Because the Higgs interacts differently with up quark and differently with down quark slightly. So the down quark is slightly heavier in the Lagrangian than the up quark. So that breaks this nucleon symmetry of proton and neutron. And on top of that, electromagnetic interactions also break this. So this isospin belonging to one nucleon doublet exactly is only true for strong interactions, which is broken this symmetry slightly by electromagnetic interactions and also by what is it called, the spontaneous symmetry breaking of masses, of up and down masses. In fact, in a way, we are lucky. The neutron is slightly more heavy than the proton. If proton were slightly more heavy than a neutron, it would be all messed up. The thing is, neutron is slightly heavier. The light value is always, it has to be stable because baryon number is an exact symmetry, as we know. So proton is stable. But what happened if proton was unstable and neutron was the one who was lighter? Then we couldn't have the hydrogen atom. Because hydrogen atom is proton, electron, but if proton is not stable, we can't have a hydrogen atom. If we don't have a hydrogen atom, we don't have one. So we are very lucky that down part is slightly heavier than up part. That means that the neutral part is heavier, which can decay, but proton is stable, which gives us the hydrogen atom and all the life that we know it exists. And that is, I think, in part due to the fact that neutron is very slightly heavy. Thank God they're not exactly the same size or slightly the other around. Yeah. You wanted to ask for them?
Yeah, so just wanted to ask, as you said that the theoretical predictions are of smaller precision compared to experimental, especially going forward, right? Than equal to 28 experimental precision VFPs. So what are the challenges exactly, that are preventing us from increasing theoretical precision?
You see, there are various ways. There are various contributions come from all different interactions. Quantum electrodynamics gives the most significant effect, but that is very well under control. We know exactly how they will contribute even to sixth order.
Yeah, you can do that quite prediction.
Yeah. The same is true for weak interactions. Weak interactions, in fact, contribute as one order of magnitude smaller than the QCD interactions, but still they are under control. People know it about two levels, And the 3 levels, only the leading logarithms results are known, but they're still sufficient. It's the QCD part which problems.
Basically, the strong interaction step.
And also this vacuum polarization diagram. They are hard to come. And so when the precision increases, maybe the other diagrams should be calculated more precisely as well. This is one of some of the projects that we want to run with some of the students in, here at Lance. If they can help us calculate some of the contributions which hadn't been calculated, but they may become essential once the result from the next generation.
Some diagrams are very important for it.
They may become relevant when more precise experimental results are available. So I hope some of them can be calculated.
Yeah, let's hope so. I'm looking at you, Josefa, right now. Or somebody else. Or somebody else. Yes, please go ahead.
Yes, sir.
It's like fortunately or unfortunately, my specialty, but since very school, so I'm definitely much younger than you are, at least by a few months. Yeah. My question is that you keep visiting Pakistan. You've been to religious institutions and stuff. Those which are there in Salam and Parliament Council. So what do you think about the status of physics that you teach? That's your field. What kind of talent do you see here? What can be done to the things here that can contribute nationally and internationally?
Yeah, that's a good question. Do I have to answer?
Because you have huge experience, you know, lived all over.
Yeah, I said we're going to make you answer all the questions.
You can record it.
Yeah.
Yeah. I think people are making efforts. Always more efforts which are needed. And if we think of improving what is happening in the country, physics and other branches of fundamental physics, it's always nicer to blame someone else. That's what I'm going to do as well. I think one of the things which is quite important is to strengthen the understanding of concepts of science at the level of school, the colleges. Because once you reach the universities, do not have very well qualified students who will start their master's thesis or PhD thesis, then it becomes very, very hard to train them. And once if they're not very well trained, and if they still get their degrees, then they will be the ones train the next 30 generation. And this becomes very complicated. But having said that, it doesn't mean that we shouldn't try to make the best of what we have. So yeah, after Salam, I still believe that we have had a lot of very well-known physicists who play a very important role. Most of them stayed outside the country. He graduated with one of those, Kessler Sheffield, who still works in Delaware, who was one of the students of Salam, worked for value integration models. And there is another in Germany who was also there present at NCT last week. And there's two others who then take students and graduate them and hope that somebody. Students, exceptional students like Salam, doesn't always happen, but then I have been involved in the supervision of the students and to continue to do that, but suddenly there are some students give you a lot of surprise that they can become very good, and you have to be very close to all the time. And because exceptionally good students not found all the time. For example, I started working with a master's student only a few months ago, and I was working with a postdoc that I had in Spain and with this master's student. But then this master's student from doesn't happen here. He started asking questions which were very deep and fundamental. And in fact, I had ignored those questions in some of the calculations, and he made me realize that we should have done. And he was only a master's student. So there is personal effort, but I think that the effort should be in two things. One thing is appointment of lecturers and professors. This is a very important subject anyway, because whoever you will hire will be teaching many generations to come. If you don't have someone to hire, don't hire. But do not give the job to someone who can't do his or her job, because that is messing up the education. And the same for sometimes we want to have PhD students, this and that, because that looks good that people are graduating PhD students. But we should really see if some PhD student, they should be interviewed, see what their level is, and do they have the potential to become world leaders by the time they finish their PhD? You can assess that to some extent. You can have surprises that get all the stuff that can be done. So we have to be very careful on that. And I think that many institutions in our country have not been careful about that. Yes.
So dedicated to have the person obviously just will be answering this question, but to follow up from what you asked, what's the status like in Latin America and the countries that you work in? Are they similar to Pakistan with this system, with the education quality?
Mexico is doing very well. I think Mexico is doing very well. The economic conditions look quite well, so we get a lot of funding as well. And some of the students that I get with there. Okay, yeah, this is one thing I want to mention. That in NCP school, some of the people who are giving these invited talks and lectures are in their 80s. So you wonder why we have not been able to produce better students than us who can actually come and take our place. And those speakers are 30 years old or 40 years old. Why should I be giving it at my age? And that doesn't happen in Mexico, for example. I graduated 11 students and PhD students, and some of them now, people ask them to give review talks or plenary talks, not me, although they know a lot more than I do. So they have managed to use very few students can take that line. And that, in part, is the training that is done at the undergraduate level and at the school level, which I think from Central America is different. They are like us, Fernando basically came on there. It was very good. But then again, there is exceptions like him. So their system has to be compared to ours. But then other Latin American countries, for example, Brazil is doing very well. In some cases, it does even better than Mexico. Argentina does very well. I think Chile does very well. Colombia does very well. The system of education in Colombia is very well, extremely good. For example, if their students come and talk to me and say they want to do PhD with me, and I said, this is going to take me trouble. So I have to prepare myself a lot. For he's going to ask me questions that is going to keep me sleepless. Right? But it's challenging and it's also developed a hard work for me. But it's good that that's how the youngsters should train. They should be able to challenge rather than just follow what you're saying. And then you're the one who's the boss of this. That's it. Doesn't progress. No progress.
The second question is about equal access. So what I inferred from what you said is that in Mexico and Brazil, every student goes to school, same kind of schooling system, everyone has expectation. So what we see in Pakistan is this dichotomy of schooling systems, there are different kinds of courses, kind of education gets linked with financial and economic status. Kind of students who come to us, for example, especially economic backgrounds mostly. So is that also contributing because our filters are very narrow?
I think I understand your question. And I think let me go out of Mexico and Latin America for a moment and then go to Spain where I have something different. And which I think makes a lot of difference is that when I meet my fellow professors in our state university, which is a public university,
And I see so much dedication in teaching that is absolutely wonderful. The students don't have to pay almost anything in the public education in Spain, but they get the top class teaching, research, supervision. Because everybody goes to teach with a lot of sense of responsibility. Now, this subject that I'm teaching, by the time he comes out of it, he has to be an expert. And that I don't see in my classes. And probably I don't, I didn't say a lot in Python, but sometimes I see that kind of dedication probably is not existent in everywhere. It does exist, but not everywhere. Once you have that, and once you're able to produce those students from everywhere, public university has the same opportunity or similar kind of dedicated and teachers who know a lot, private, but it's not. Yeah, I think that should be addressed somehow. I think that sometimes, many times it also happens that, when you're getting a lot of economic benefit, and that's what many people also think, if I'm being paid, being a teacher now, so I get that. Why do I get to teach kids and opportunity to pay more and less? One thing is that it should be improved. It should be more homogeneous so that people can go everywhere with people. Secondly, sense of responsibility. For example, one of my Chinese friends, he comes from a small village. He had all the opportunity. He went to Parliament. He did a very good postdoc. He was given on his needs. Supercomputers to use that in the homework scholarship to children. He was being offered a position in Germany. He said, no, I'm going to go back to my village in China because they need me more than you need me there. I'm going to take it back to my China. So there is a sense of responsibility and commitment as well, which I think some of us have to have. It's not always that somebody will make this. It's something that you sacrifice yourself or make that. And I think that's quite important.
Okay, so I'm going to take. Just 1 second. We can come back to you. We're not letting him go before he answers all the questions. We're going to make him answer all the questions. I just want to take a couple of questions from the online audience. So Sajjad Saab has raised his hands and I've asked him to unmute. Please go ahead, Sajjad Saab.
Thank you. Adnan, let's go back more than 3 decades, I guess. I'm happy to see you in this talk and even otherwise, but I'm very happy that you still have that mischievous streak in you. It doesn't give any teacher any more pride than to see a student who has gone far beyond the teacher himself or herself for that matter. I don't have a question as such. I just wanted to commend you for all your efforts and I wish you well. Thank you.
Thank you very much, Sajjad Saab. He was my professor at Qadir University. My master's, one of the first courses I received was from him on mathematical methods in physics. And he's talking about me being mischievous because I think those were the times we used to be more mischievous and used to do things which are probably to some extent inappropriate as well. But I'm happy that you were able to put up with us, and I think he was one of the best professors that I've had in the Qadir University. Thank you very much for being here, Sajjad Saab.
Thank you, Sajjad Saab.
You're welcome.
All right, so we have a couple of physics questions here which somebody had typed on the chat. I'm just going to read them off and you can maybe give them an answer. So one question was, what is meant by gives off energy when an electron changes its energy level? How does this process occur? Well, so I'm gonna.
I have no idea.
Yeah, I mean, this was a long time ago. Somebody asked this question, but this was on the chat. But then this other question is, what is the theoretical prediction of the muon anomalous magnetic moment according to the Sun model? Again, that's a number. Maybe you can just look it up.
But I can actually answer that question a little bit. So sometimes people ask me, because electron is the most stable particle, have people made prediction for the anomalous magnetic moment of the electron instead of the muon as well.
Yes and no. When you calculate the anomalous magnetic moment of the muon, what we need as an input is the interaction doubling of electrodynamics. And that is computed using the anomalous magnetic moment of the electron. So you use the anomalous magnetic moment of the electron to find what is your electromagnetic coupling, and then you use that as one of the inputs to calculate the anomalous magnetic moment of the muon. So yes, Salam model predicts makes prediction for all three of them, and experiments try to measure them as precisely as they can. So I think I gave those numbers. If you can write to me at some point, I can try to give you the recent numbers for each of them for tau, muon, and electron. I can look up the literature and later send it to you.
Okay, great, thank you. But also an excellent resource is PDG Live. You can just go there and check up the numbers yourself as well.
There is an interesting thing I would like to mention it that people can ask, what about quarks? Do they have anomalous magnetic moment? Or in fact, do they have anomalous chromomagnetic moment because their interaction is slightly different? And that's, I think, a very interesting question. And this is one of the things we are trying to answer. And if you define the anomalous chromomagnetic moment exactly as you define the anomalous magnetic moment, you find that it doesn't even qualify to be physically observable because it's gauge dependent and it's infinite. And because the triple gluon interactions that take place at the quantum magnetic level. So one of the things we're trying to do is to have an identical or similar definition, but different from the way it is defined in QEs. Yeah.
Right. Do we have any more questions from the online from the people present here in the hall? You, I know, have had a comment, so I'm going to come. Does anyone else have a question? If not,
Dr. Adnan, Salam alaikum. I'm here in Institute of High Energy Physics in China. So nice to see you and wonderful talk.
Thank you.
So I just want to, because I am an accelerator technologist. I am working on
Are you in Best
CEPC.
3?
No, in CEPC, accelerator technology. You remember you visited, yes, you visited before. I was working in CHEP, PU, and then I moved to Institute of High Energy Physics. So I just want to know, this is just for my information, I am not a particle physicist, but I work on accelerator technology. To my information, can this SCCEE and CEPC can solve this muon G-2 puzzle? Will they have some contribution on
That's
that,
exactly
or
what I'm trying. That's exactly what I'm saying, trying to say that there is no puzzle. People had been thinking for the last 25 years that there was a puzzle. I don't think there is a puzzle anymore. So there is nothing to be solved. It's all solved.
Okay. So what
It's a big
about
statement. Maybe not many people will agree with me. Me saying it's so definitely it's all solved. Because I wrote this remark on, I don't know, some particle physics girl is doing some sort of string theory model. And she was talking about this anomaly. And I just wrote that, look, hold on, this was an anomaly some time ago, but it's not an anomaly. But she just burst into flames. And I thought, well, I just had to tell her it's up to her to look up the literature or not. I didn't say anything else. But I don't think there's an anomaly at the moment. In fact, there is some point there was considered to be an anomaly, which is the MW mass. The prediction was not exactly matching the initial experimental measurement. I think it was in CDF. But then later results have again told us that that anomaly has been removed. I think the situation in B physics is also more or less under control. And most people believe that if you just do your QCD calculations right, then standard model is okay. There are no such anomalies, no such differences, no such noticeable differences between standard model predictions and the experimental results that we should worry about.
So if we wanted to quantify that, looking at thousands of observables, the standard model best fit values can only give deviations which are between 2 and 3 sigma.
Exactly.
And those are the larger deviations that we'll
Yeah.
talk about.
This was one of
And-
the largest at some point. But
Yeah,
then-
yeah, because this was like this went to 4 sigma plus. But so this is precisely why if you're a particle physicist, you are naturally more conservative, and unless it hits 5 sigma, you don't get overly excited about it. You only begin getting excited about it when it hits 4 sigma, but 2 and 3 sigma is.
And this is true that whenever QCD is
That's what it
involved,
is.
even when it is about 4 sigma, people still are hesitant to say it's discovery because they know that
Yeah.
things might have got messed up. And like, those people who must have remembered that in 2012 Higgs was discovered. One of the biggest problems in discovering the Higgs particle was that again the background noise which comes from the strong interaction physics that I'm talking about, QCD, was huge. So the main signal of Higgs particles was swamped by the whole noise there. So people had to do 2-loop, 3-loop jet calculations to remove the noise which comes from QCD interactions. By doing the calculations, subtract it, and then they could see the Higgs signal. So yeah, QCD has been causing problems for a long time, but those calculations required mostly perturbative calculations. Time taking, but still conceptually easier to do like any other. But here the non-perturbative part comes, which people have still not learned to solve. The only thing we can do in any kind of physics is always perturbation theory, where the coupling has to be small so that we can make a systematic expansion and do the calculation order by order. But when the interaction becomes stronger than one, and when you cannot make that expansion in perturbation theory, then we still don't know how to solve that physical system. And this has been, you can say that in certain sense, an embarrassment for physics for many, many decades.
Okay, so I just wanted to make one final comment. It's tangential to your talk, but because you mentioned Fernando Quevedo, I would also like to point out that he was also the do they call it director for the ASICTP as well, sometime in, I think, around 2014 or so. And personally, Edo is the person who taught me supersymmetry when I was doing a course in Cambridge. So I have fond memories of that particular course, and I also wrote an essay with him.
And his patron labs. He was.
Oh, he was here as well.
Salam lecturer.
Okay.
I think I have seen that he was at LUMS. Which year was he?
While he was the director.
Oh, okay. In fact, because I was organizing the school, I think once he was going to visit Costa Rica. And at some point, somebody told him and he said, Adnan, can you come to give us on what you're doing in Central America? And I had almost no free time to visit. So I remember I took a plane, I flew to Costa Rica at 3 a.m, gave my thing at 9 o'clock and came back the same day. So it was just a very, very rushed up meeting in Costa Rica with Quevedo. But I realized the way he was working with different groups in different parts of Central America, how much effort he was making. And he was taking up a lot of students from different parts of Central America, and he was literally very concerned and trying to help out the region very much.
Right. So I'll give you the final word, question, comment.
Who's the guy? The Guatemalan guy who was on tequila while he took this.
Oh,
He has been
right here, this guy.
Yeah, Adolfo Cepeda, he's a Mexican, he was a Mexican theoretical physicist. He in fact did his PhD from I don't know where in USA, but his supervisor was also Mexican. It was Rocky Day, who died I think in 1980s. But he was a leftist at that time, Adolfo Cepeda, and he worked in one of the most prestigious universities in Mexico. His area of research was in part started with what I used to do, UCD. He worked on chiral centrifugating, one of the most famous papers in this field. That is where MCDP was made. It was made the first director of MCDP. So he moved from his institution in New Mexico City
moved to Chiapas, which is a much poorer state, but he decided to leave everything there, go there because he wanted to make a difference. When he moved there, he was already around 80 age, but he was so active. The first school that we did in Guatemala, I remember I was giving some lectures, so I generally wake up early. But he would be sending email to me at 3 in the morning. Have you done this? What's the photocopy? Who's going to make it? And I was trying to him, why are you up at this time? You should be sleeping. It's 3 in the morning. But even at that age, he would just want to do everything right. And he would wake up at 8 in the morning and he would be lifting tables and say, no, if you do this at 8, then the students can listen to it better. I said, hold on, you hold your horses. Somebody else can do it. But he was extremely impatient. But I think during the time we lived, he really made a very good contribution. People like this, I think we need everywhere.
The reason I asked about this is that if you could take Hafizah or tequila in Pakistan, we might be able to get this kind of an institute here in Pakistan. So please don't record it because I might be received by a black dollar.
It's already recorded. It's going up on YouTube soon. You make arrangements. That's on you. मैं आपको नहीं जानता.
I don't know.
Which is true. मैं आपको नहीं जानता. I have to give that disclaimer, yeah.
The director of LCTP in Mexico is Luis Felipe Rodriguez. He's an astronomer, not a particle physicist, and I think he's going to play an important role. One of the things I mentioned, I wanted to mention that one of my previous PhD students when she's working at MCTP, and what I like very much is that they have also started what they do at ICTP, like the diploma course. So they do the diploma course for Central American students who come to Mexico for 6 months and a year, and they give them lectures for that year to prepare them for advanced studies. And not only this, she used to tell me that because Chiapas has its own rivers and jungles, and there are many communities which are not directly linked to roads. And sometimes they go and try to teach science experiments to students, but they have to go through a boat because there are no roads to go there. And they take the equipment there and they teach students what happens in science. And I think this is a great effort and commitment on behalf of some of the youngsters who want to do that. And that is done in MCTP. It's not needed in ICTP because there is no such problems. But MCTP is playing a role for advancing science in that their proper region as well, which is quite impressive. I feel quite proud of what they're doing.
Okay, well, like all good things, this too must come to an end. It was a genuine pleasure to have you, and you have kept us here for 2 hours. It didn't seem anything more than 10 minutes, frankly. So it was a wonderful session, and I hope the students and the faculty enjoyed it and learned a lot from it. I certainly did. Thank you very much.
Thanks, Steve.
And thank you to the online audience as well. Please watch out for the remainder of the Salam series.
And the students that we talked to before the lecture, you can keep in touch with me.